In this class, we are going to discuss about combinational logical circuits. And here, examples of combinational logic circuits. Those are adders, subtractors, multipliers, dividers, multiplexers, demultiplexers, and decoders. Adders. Adders are designed to add two single-bit numbers. Adders are arithmetic combinational logical circuits. Adders are two types, half adder and full adder. So here, for a half adder, you may have two inputs and two outputs. Those two outputs are called as sum and carry. So now, how can we get the circuit for the half adder? That's not a problem. We can see in this following video. So here, first you can see the block diagram of the half adders, and it's contain two inputs and two outputs. First of all, we need to observe the problem definition. So that means here, what half adder is going to add? Two single bits. What mean single bits? When the number is contained one digit and it's called as single bit. For example, A is equal to either 0 or 1 and B is equal to either 0 or 1. I label the input as A and B and I need two outputs. They are called as sum and carry. Now I'll design the truth table for half adder. With two inputs, you will have four combinations. So now A and B are the inputs and sum and carry are the outputs. So the four combinations for the AB are 0, 0, 0, 1, 1, 0, and 1, 1. Now I'm going to add those. So first, 0 plus 0 is equal to 0 and we didn't get any carry. Then 0 plus 1 is equal to 1. Here also we didn't get any carry. 1 plus 0 is equal to 1. Here also carry is equal to 0. Here 1 plus 1 is equal to 0 and we have 1 carry. You can remember this binary addition. 1 plus 1 is equal to 1, 0. So this is called as sum and this is our carry. The next step is we need to consider K-map. Here you having two variables in output. So for each output, you need to define a K-map. By using K-map, we are going to take the expression. First, I'll take K-map for sum. Here, how many input variables are there? There are two input variables. So, I'm going to have a K-map like four cells. Here, 0 and 1 are the variables and I have A and B. Now here, you can check where we get 1 for sum for the A is equal to 0 and B is equal to 1 combination and A is equal to 1, B is equal to 0 combination for like this. I want my expression in sum of product. That's why I'll take 1. If you want your expression in product of sum, you can get the 0. Now, here you can do this diagonal grouping. Diagonal grouping is XO. Otherwise, you can check in another way. We can individually group in this one and this one. So I'm going to write this. In here, we have A, B bar. And here we have A bar, B. So now we are going to draw the K-map for carry. Now here we have only one carry and the combination is A and B is equal to 1. So I can write A, B. So here I'm going to draw the logic circuit for half adder. This is B. And I have an XOR gate here. And this for sum. And this for carry. Now we can check the input and output in Logisim software by using the truth table. So now here we have both 0 for both A and B. So we didn't get a 1 for sum and carry out. Now I change the B into 1. We get 1 for sum. And I'll change both the 1. Then I'll get carry as the 1. So this is the explanation about half adder. Now I'm going to move to the full adder section. Previously, we discussed about half adder. Here, we are going to discuss about full adder. Full adder is also a single bit adder like half adder. But we choose full adder because we have some limitations in half adder. Those limitations are, example, when we add 2 bits in next step, if you are having any carry along with that 2 bits, you are not going to add with the half adder. In this case, you need to half adder to add another half adder. But for second half adder, you are used it to add 3 bits. It's not going to add 3 bits. In half adder, adding of carry is not possible. That's the limitation of half adder. To overcome the limitation, we are having full adder. Full adder is always similar to half adder. The only advantage factor in full adder is having carry addition. That means whatever 2 inputs in the half adder, those are increasing to 3 bits. The third is a carry from previous bit. Here you can see the block diagram. In this block diagram, you can observe here 2 single bits and 1 carry. This is a full adder with three inputs. Two general input, one is carry. Those are outputs, sum and carry. Here also carry, here also carry. That's why I named input as carry in and output as carry out. Now we will see how to design a logic circuit. First of all, we need to identify the problem definition. Full data contains three inputs and two outputs. In these three inputs, we may have 8 combinations up to 0 to 7. Now, I'm going to draw the truth table for full adder. Now, these are the 8 combinations for both these are the 8 combinations for 3 inputs. Now, I'm going to add those combinations one by one. In this procedure, I am at A with B and the result is added with C in. In any addition, if you had any carry, place 1 in carry out. So here 0 plus 0 is equal to 0 and the result 0 plus 0 is equal to 0. So I didn't get any sum or carry here. Then here 0 plus 0 plus 1. So I get 1 for sum. Here also 0 plus 1 is equal to 1. 1 plus 0 is equal to 0, 1. So I'll get 1 for sum. And here 0 plus 1 is equal to 1. So please remind it. I'll put the 1 here. And here now 0 plus 1 is equal to 1. And here 1 plus 1 is equal to, I'll get 0 for sum and 1 for carry out. Because 1 plus 1 is equal to like this. So this is for sum and this is for carry out. Here 1 plus 0 is equal to 1 and another 1 plus 0 is equal to 1. So here also no carry. And here 1 plus 0 is equal to 1 and here 1 plus 1 is equal to sum is 0 and carry is 1. Here 1 plus 1 is equal to, I got 0 for sum and I have a carry as 1. And here also 1 plus 1 is equal to 0 and I have a carry and 0 plus 1 is equal to 1. This is the truth table for full adder. Now to design a logic circuit, you need logical expression for the relation. Here to design any Boolean expression, you are making use of K-map. Here we have 3 input variables, so 3 variable K-map. When taking 3 variable K-map, when you take 3 variable K-map, make sure the number of cells. Here 8 number of cells. First, I'm going to take the K-map for sum. Now, I have 8 cells and 0, 1. Then here 0, 0, 0, 1, 1, 1 and 1, 0. Now I'm going to write the output of 1 in here. You can check 0, 0, 1. So 0, 0, 1. Here I forgot to put B, C in. Okay. I'll change the color. Then 0, 1, 0 here. Then 1, 0, 0, 1 for A. So I'll put here. Then 1, 1, 1. Now we have two diagonal grouping. So now for sum, I'm going to write like A XOR B XOR C in. Now I'm going to check the carry out K-map. I will put those combination 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So I'm going to have three grouping. First group, second group, and third group. Now, for the first group, I have A, C in because B is changing as 0 to 1. So I can't write in this K-map B. Then for the second grouping, A is changing as 0 to 1. So I can't write this A. So B, C in. Now the last group. Here A is didn't change and B is also didn't change. Now those are the addition between this expression because it's sum of products. Now I'm going to show you the logism diagram circuit design half and for full ladder. Sorry, for full ladder. Then I'm going to check the truth table also. Here, this is the circuit diagram for full atom. Then I'm going to check some random combination for last combination. All are 1. Then I have sum and C out are 1. Then A and C in are 1. So I get 1 for carry out. So this is working correctly. Now I'll move to the next section, subtractor. A digital logic circuit called a subtractor is frequently used to subtract numbers. Subtractors can often be divided into two categories. Those are half subtractors and full subtractors. Using full subtractor, we can perform difference between 3 bits. Initially, we are having half subtractor. So by using half subtractor, we can perform subtraction between two single bit numbers. If any borrow is occurred to the next bit, then we need to perform subtraction between 3 bits. So half half subtractor is not going to perform that operation. For example, if you are having A like 0, 0, 1 and B like 0, 1, 0, and then 1 minus 0 is equal to 1, and here 0 minus 1. We need to consider 1 with borrow 1. For third half subtraction, it is impossible to perform subtraction. This particular limitation can be overcome by full subtractor. Full subtractor is a combinational circuit used to perform subtraction among 3 bits. So, this is the block diagram of the full subtractor, which is having 2 input bit with the borrow input. So here these two are the single bit numbers and this is borrow input. Totally 3 inputs and 2 outputs. Those outputs are different and borrow out. So now to design this functionality, we are going to consider truth tables to satisfy full subtraction. So these are the combination for 3 inputs. And now I'm going to subtract those. So here 0 minus 0 and 0 minus 0. So I didn't get any different though borrow out. And here 0 minus 0 and 0 minus 1. So we need to consider 1 with borrow 1. And here also 0 minus 1. So 1 with borrow 1. And here 0 minus 1, we having a borrow 1. So I put it here and I have a different 1. And here another 1. So 1 minus 1 is equal to 0. And here 1 minus 0 and another 0. So I have 1 for different. And here 1 minus 0 is equal to 1 and 1 minus 1 is equal to 0. So I didn't get any borrow out. Now 1 minus 1 is equal to 0. 0 minus 0 is equal to 0. Here is also no different and no carry. And here 1 minus 1 is equal to 0. Then 0 minus 1. So we need to consider 1 with borrow 1. Now I'm going to define a K-map. For the K-map, we have 2 outputs. So we want to get K-map for both different and borrow out. So first for different. Now for different, we have 0, 1, 0 and 1, 0, 0, 1, 1, 1. So this is the diagonal grouping and we have 2 groups. Now I'm going to write it as A XO B XO B in. Now for the borrow out K-map. here 0, 0, 1. Then 0, 1, 0. 0, 1, 0. Then 0, 1, 1. 0, 1, 1. And last 1, 1, 1. Here also I have 3 grouping. For the first group, A bar, because A is 0. So I want to put A bar and B in, because B is changed as 0 to 1. For the second grouping, A is changing, so B, ignore my handwriting. Then third grouping, another A bar, and here B is didn't change and B in is changed to 1 to 0. So A bar B. Now I can write A bar B in plus B in plus A bar B. Now I'll move to the logism design for full subtractor and for the truth table in the presentation slide. Here I'll try to check some random combination. So I'm going to check the 7th combination and it's 1, 1, 0. So 1 for A and 1 for B. I didn't get any change in the output. So both are 0. So now I'm going to check the A is equal to 0 and B is equal to 1 and B input is equal to 1. Now here I got 1 for borrow out. So it's working correctly. So this is the logic design and truth table identification for the full subtractor. Now I'll move to the next slide. Multipliers. A digital logic device called a multiplier is frequently used to multiplying numbers. The combinational circuit for the multiplier must be designed using 4 AND gates and 2 half adders. The multiplication will be done by the AND gate and the product terms will be added by the half adders. Now I'll show you how to draw the multipliers in Logism software. So I want 4 inputs named as A0, I'm going to copy this. A1 and B0, B1. And I want 4 outputs B0, C1, C2, C3 are following. And now I want 4 AND gates with 2 inputs. And 2 XOR gate. Now I'm going to connect the wire properly. This first AND gate with A0 and B1. And the second AND gate with A0 and B0. Third AND gate is B0 and A1. And the fourth AND gate is A1 and B1. Now I'm going to connect the others using wire. Then it's going to this first XOR gate, and this directly go to the C0 output. And now okay. Now I'm going to take some outputs for inputs. Then the last combination, I choose hand icon, then all are 1. So I got C3 as 1 and C1 as a 1. So you can check it here. Now I'm going to say take the okay. So A1 is 0, others are 1. So here C1 is 1 and C0 is 1. So it's working correctly. Then another combination, A1 and B0 is equal to 1. I got 1 for C1. So it's working correctly. So this is the design for multiplier and truth table is here. Now we want to see the next topic and dividers. The dividend, divisor and quotient have initial n-bit values. The dividend comes after the first partial residual n zeros. The basic division method continually divides the quotient into consecutive bits, starting with its most significant bit. Applying the following division step, the partial residual should be moved a little to the left. The divisor less the divisor is the partial remainder. Should the new partial remainder be positive, relocate the quotient and new partial and set the new quotient bit to 1. Remain slightly to the left. If the revised partial remainder is unfavorable, the revised set the quotient bit to 0 and replace the old partial remainder with the current one. And the quotient needs to be slightly pushed to the circuit. And the quotient should be moved one bit to the left. Once all of the bits in the quotient have been produced, repeat the divide process to produce the quotient and remainder. This is the circuit design for divider. Now I will show you how the divider is working. Here we are going to divide this number digits by down this number digits. And here I put 1 0. So I have 2 as the decimal point and here I have 1. So when I divide 2 by 1, I got 2 numbers and 0 balance. And here you can check, I'll change it to 3 and I'll divide 3 by 2. Here 1 time and I have 1 balance. By this way, the divider is work. You can design the dividers by using logisim. Now, in this class, we discuss about half adders, full subtractors, multipliers, and dividers. Now, we will see in the next class. Until goodbye. Thank you.